A very good afternoon to all of you. Let me start the lecture. Okay, today I will talk about convection heat transfer, and in this sequence, I will talk about boiling condensation as well. Okay, so this is the entire range of topics related to convective heat transfer. So let's discuss about this. So today we are going to talk about convection heat transfer. When I was discussing about heat transfer in general, I told you people that this is governed by Newton's law of cooling. Okay, Newton's law of cooling, right? What is that law? That law states that flux, double dash means per unit area, dot means per unit time, is equal to H. Suppose you have some body that is heated and that body temperature is higher than the surrounding temperature, surrounding fluid temperature TF. So heat flux is given by this. Graphically, you can present it like this. Okay, this is suppose you have the body and its temperature. Let's say we are representing T body. Somewhere in some book you will find its representation T wall, and somewhere you will find Ts in source of heating. So this body is hot, higher temperature. Now surrounding this body, there is a fluid. Surrounding this body, you will find there is a fluid, right? Now this fluid have lower temperature. Sometimes we call this fluid temperature as TF. So in some book you will find this is written as T infinity. So this is then heat transfer. If TW is greater than TF, then the heat transfer will take place in this direction, higher temperature to lower temperature. And that heat transfer is given by Newton's law of cooling. But so far we have discussed H so many times, but I have not discussed yet how to find this heat transfer coefficient. How to find this heat transfer coefficient. Heat transfer coefficient. Now, in the most of the cases, we find it through experiment. Experiments. Very less theory is available regarding this. We use some experiment to find out the value of heat transfer coefficient. Am I audible? Am I audible? Anyone
Yes,
please
sir.
let me know. Okay. So these, so for convection to happen, two things. One, you must have solid, and second, you must have fluid. These convection are of two types. One is forced convection, and other one is free convection. Free convection. Now, let us link with our previous topics. Now, I taught you people the fins. In the fins, we have used the H as a boundary condition, heat transfer coefficient as boundary condition. So, convective boundary condition was specified. So, convection boundary condition was specified. Somewhere else we have used also when we were discussing the resistance concept. We have used heat transfer coefficient. Okay, On this side, suppose fluid is there, and on this side, fluid is there. So suppose HL, left side heat transfer coefficient, right side heat transfer coefficient. This is the solid. Then I told you that suppose this is the temperature, and then in this direction temperature, then this solid, and then this heat transfer. Several resistances, convective heat resistance, then solid heat resistance, and then again convective heat resistance. Now suppose here is the temperature, bulk fluid temperature, let's say TL left side and right side, and TL and TR, and we have used right here 1 upon HA resistances, 1 upon SLA, and 1 upon similarly H or A, and here the resistance related to the wall. We have used conductive resistance. Now see here also we have used S, but S was given to us. So we have not discussed yet how to find these values of H. So how to get these values of H, we will discuss it a bit. Let me pause for a minute, and I am coming back. So far, we have not discussed how to get the value of H. So today's discussion will be confined to how to get the value of heat transfer coefficient. All right. Am I audible now? Yes, please. Hello. Am I audible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, okay. So we have used H as different places, but unfortunately, we have not discussed how to get the values of H. Okay. So we have waited so long to discuss this concept of convective heat transfer coefficient, and today we will discuss this concept of heat transfer coefficient. Now, please tell me, while discussing the heat transfer coefficient, just wait a minute, please. Yes. So these convection heat transfer, the precursor is you must have solid, you must have fluid. All right. Now these convection are of two types. One is natural convection, and other one is forced convection. Forced convection. Natural convection meaning natural convection. What do you mean by natural convection? That will happen naturally. So what happens? Suppose this is a globe. Very a simple example I will take. The rainfall everybody understands. Suppose this is the Earth is spherical almost. Now at this globe, some part of the Earth is heated up due to sun rays, direct falling sun ray, or it may also happen some ocean current, warm ocean current is going alongside. So thereby heating up this region. Now in this region, if heated up, what will happen? The molecules, air molecules near this, okay. So as you heat something, it is the general tendency that it will expand. So once it will expand, its density will decrease. Its density will decrease. So while you increase the temperature, what will happen? Density will decrease, and hence the particle, hotter particle will move up, and the particles who have less temperature will come down due to higher density. And in this way, heat transfer take place in natural convection. Now, the rainfall you can explain on this basis, because you know why rainfall. Suppose this is the water body. This is the water body, and suppose this is some mountainous region or western Ghat or some hilly regions. So this is the water body. So air is moving from this side. What will happen? Air will moving this side. It will gain the moisture from water. Okay, it will gain the moisture from the water, so it will have the moisture in the form of vapor, because this area, liquid area, will be heated up. So the vapor, liquid will be converted into vapor, and this vapor will be mixed with the air. Well, this vapor will mix with the air. Now, uh, when this vapor laden wind will strike on this high mountainous region, what will happen? That it will rise up. Once it will rise up, you know, once you go upward in the atmosphere, what will happen? Temperature will decrease. So temperature will decrease. So once temperature will decrease, see here higher temperature, so it will rise up due to less density, and once it will rise up, its temperature is going to decrease. So all vapor in the air will condense. If some condensating, if some particles exist in the atmosphere, it will condense over there. Some particle, it will condense over some particle. Okay, you know there are a lot of pollutants in the atmosphere, so condensation will happen. So I will discuss in the boiling some nucleate reasons should be there. Just like condensation to happen, some base surface must be there. Boiling, if boiling need to take place, then also we must have some surface there. So condensation would take place due to decrease in temperature, and then vapor will be converted into a liquid, and then rainfall take place on this side of the mountain. Okay, and on this side you will find rain shadow zone, because once air uh, this all the moisture, all the vapor will be converted into liquid and fall into the surface on this side itself. So whatever air go on this side, it will be dry, and this is called the rain shadow zone. Rain shadow zone. So this is the very basic example. Rainfall, rainfall, natural convection, convective currents of wind will bring the rainfall for us. So how much important this natural convection is. अब आप क्या लेते हो? एक कप में अगर चाय ले लो, यू हैव द कप, और ये पकड़ने वाला हम बना दे रहे हैं. माई ड्राइंग इज नॉट गुड, सो यहाँ से अगर आप पकड़ते हो इसको, यहाँ पे चाय रखी हुई है, तो नो एयर इज मूविंग, एयर इज मूविंग, सो हीट विल ट्रांसफर. अगर यहाँ पे चाय, गर्म चाय रख दो, तो आफ्टर सम टाइम यू विल फाइंड दैट दिस टी विल बिकम कोल्ड, because heat has been transferred from tea to air moving above the cup. Okay, so these all are natural convection example. Now let's take the forced convection example. In natural convection example, what happened? You have the hot surface, uh, you have the hot surface, and a hot surface, so air molecules, so due to high temperature, what will happen? Density will decrease, so it will rise up, and whatever cold molecules are there, they will go down. Once it reaches right here, it will pick up again the temperature and rise up. So in this way, you know, you understand that heat is being transferred from bottom to top. Okay, so due to density difference in the natural convection. So in this way, you must understand that in the natural convection, the density difference is very important parameter. Density difference is very important parameter. Now, some dimensionless parameter I would like to discuss, because dimensionless parameter is very central in this. convective heat transfer process. So what you mean by dimensionless number? The number that is in the numerator and denominator both you will find the same dimension. So both the dimension will cancel out, and hence you know and hence both the dimension will cancel out. Suppose dimensionless number कैसे define किया जाता है? न्यूमरेटर में जो क्वांटिटी लोगे और डिनोमिनेटर में जो क्वांटिटी लोगे, both have same dimension, so dimension will cancel out, so this will become the dimensionless. Now the natural convection, as far as the natural convection is concerned, heat transfer by natural convection is more complex to analyze than forced convection. Okay, forced convection, a brief idea I am giving to you that you have solid and fluid for convection. Okay, now fluid, if it is naturally moving, then this is natural convection. If we move this fluid, movement of this fluid caused by some fan, blower, compressor, etc., then this will be the forced convection. Suppose I put the fan right here, and due to this, the air is blowing. Okay, and there is a hot surface, so you will find this is the forced convection. So let's discuss a bit about this also. So heat transfer in natural convection is more complex to analyze than forced convection. The reason is that uh, uh, यहाँ पे हम अगर फैन यूज कर रहे हैं तो वी नो द velocity profile related to this fluid as a priori. But in natural convection, since this is the temperature, since the fluid motion is caused by this, right, caused by temperature difference, so we don't have any idea priori as a priori for the velocity. So here, due to density difference, buoyancy difference is created. Buoyancy force is created. So the motion is generated due to the buoyancy force, and hence the temperature distribution plays an important role in determining the motion right here in the case of natural convection. But we know the motion determines the temperature profile. So the equation of motion and energy balance must be coupled. Okay, means in a way we can't neglect anyone. Okay, so we have to solve simultaneously equation of motion as well as energy balance. Now I am discussing this topic too much late because I believe that this will require some knowledge of fluid mechanics, and you have studied the fluid mechanics so far. So you will find it will be easier to understand now. Since buoyancy force are generated due to density variation, let me discuss. Since buoyancy force is generated buoyancy force is generated due to density variation, increase or decrease due to density variations produced by temperature variation, decrease or increase. So there is one more effect caused by density variation. Density variation, see, let me write down. Temperature, due to temperature difference, due to temperature variation, you will find a density variation and density variation. So up, down, both ways. Due to temperature variation, you will find density variation, and due to density variation, you will find buoyancy force generated. Now, this is the one effect of the temperature variation. Okay. So, due to density variation, see, buoyancy force is created. Now, one more effect of this density variation, if you see. One more effect of density variation is, velocity must change. Why? Velocity must change because from fluid mechanics, you know that to conserve mass flow rates, if density is varying, then velocity must change because mass conservation. Rho A velocity is equal to constant. AV means volumetric flow and volumetric flow rate, and this rho is mass per unit volume. The mass per unit time is constant. So if density is varying, okay, and we need to have this product constant, it means A will be constant already. So what will vary? B. So velocity must change due to density variation because conservation law must be satisfied. Now so far you have, समझ में आ रहा है बच्चों? हेलो, समझ में आ रहा है बेटा?
Yes, sir.
समझ में आ रहा है?
Yes, sir.
देखो टेम्परेचर वेरी करेगा तो डेंसिटी में वेरिएशन होगा, और डेंसिटी में वेरिएशन होने से बायंसी फोर्स, एक इम्पैक्ट हुआ डेंसिटी में वेरिएशन का। दूसरा, डेंसिटी में अगर वेरिएशन हो रहा है तो टू कंजर्व द मास फ्लो रेट्स velocity must change. So there would be the variation in the velocity as well due to density change or due to temperature change, because the density change will happen due to temperature change. So this cause and effect relationship you must understand. Now, one very central parameter in all considerations regarding natural convection, since density is varying in the natural convection, so there is variation of density, you see, density with respect to temperature. So a very central parameter related to this is, coefficient of expansion. Coefficient of expansion. Why this is called expansion? Once you heat up something, so then it is the tendency of fluid to expand when heated. So that's why the word expansion. Now, why this is called the coefficient? I will discuss. Um, So this is now the density temperature variation lead to density variation. So del rho over del T at constant pressure and divided by 1 by rho, then this is called the coefficient of expansion, that is beta is equal to 1 by rho del rho or del T at P. Now you tell me that if you increase the temperature, what will happen? If you increase the temperature, density will decrease, means this del rho over del T will be negative, but beta is the coefficient, so you need to keep it positive, so we will use the minus sign here as well. So beta is equal to minus 1 upon rho del rho over del T at constant pressure. Getting it or not? So a very central parameter in all considerations regarding natural convection is the variation of density with temperature, and the change of density with temperature is a physical property, and it is a tendency of the fluid to expand when heated. That's why the name the expansion. Okay, and this property is described by the coefficient of expansion defined by the beta is equal to minus 1 by rho del rho del T at constant pressure. So hope you understand this. Now, if you understand this very easily, then I will have to move with the so that I have prepared the notes for you. Now, this screen is visible to all of you or not?
Yes, sir.
हाँ हाँ, ये पीडीएफ वैलिड है। अब देखो, वी हैव डिस्कस्ड कन्वेक्शन इज ऑफ, ये नोट्स मैंने अपलोड कर दिया है, तो आई एम गोइंग टू एक्सप्लेन नाउ। दीज आर देयर आर टू टाइप्स ऑफ कन्वेक्शन, फोर्स्ड एंड फ्री कन्वेक्शन। आई हैव डिस्कस्ड नाउ इन फिन्स, आई टोल्ड यू दैट कन्वेक्शन वी हैव यूज्ड द कन्वेक्शन बाउंड्री कंडीशन and H was specified there, given there. But here the goal is to find the heat transfer coefficient, but because we are linking with the previous topic. Okay, so to find the heat transfer coefficient for a given set of condition. Now the heat transfer coefficient H, if you recall the Newton's law of cooling, this is H Q is equal to H and delta T. So to find the temperature distribution and rate of heat transfer, you need the value of H. Okay, so this is S. Now S will depend on type of the fluid and flow velocity and type of application. As far as type of, this is the function of, means it will be given in terms of type of fluid, flow velocity and type of application. As far as type of fluid is concerned, this means the fluid properties, nothing but the fluid properties like viscosity, density, this is the fluid mechanics related properties, and thermal conductivity and specific heat are the heat transfer related property. Now, as far as the flow velocity is considered from fluid mechanics, you must know that flow velocity will define the this is the second one, type of fluid, and then second is whether you are able to see my cursor that is moving. Right? So flow velocity means either it is laminar or turbulent. Okay, दिखाई दे रहा है बच्चों? PDF is visible. PDF is visible to all of you.
Yes, sir.
Yes, sir.
Okay, so flow velocity, depending on the flow velocity, whether it is low velocity region or high velocity region, the flow can be divided into different region: laminar flow, turbulent flow. Okay, and type of application determines that whether flow is external, means flow over flat plates हो रहा है, या flow will happen over cylinders or spheres, or internal flows such as flow inside conduits, means inside pipes. Okay, the pipe may be cylindrical or parallelepiped or anything. Now I will discuss. Now first we will discuss forced convection. Forced convection, here flow of fluid is due to the operation of a pump, a compressor, or the rapid movement of an object in the flow field. I told you just before, so that is written in the notes. Q dot Q dot double dash is equal to H T body minus TL. This is the Newton's law of cooling. This is flux. I have not written in the right hand side A, because this is the divided by A in the left hand side. So is equal to S Ts minus Tf. Sometimes we represent the body in surface, any solid surface. So represents a solid surface such as flat plate or wall of or the closed conduit. Now I will tell you that uh, you are able to see this figure. This is the boundary layer. Able to see? Okay, let me tell you. Have you heard about the hydrodynamic boundary layer in your class? पढ़ा है आपने बच्चों? बाउंड्री लेयर पढ़ा है फ्लूइड मैकेनिक्स में? हेलो, हाँ, क्या होती है बाउंड्री लेयर?
सर, जब एक पाइप में आपका फ्लूइड फ्लो करता है तो जो शेयरिंग स्ट्रेस होता
Forget about the pipe. Forget about. This is the development of the velocity. Okay,
Yes, sir.
if velocity is uniform throughout, means same, no shear force, nothing, no hindrance at all, you will not find any boundary layer. Any layer will be developed there, because every layer have the same velocity, so there would be no shear stress. Because shear stress, as you're able to recall, if shear stress is defined how? Newton's law of viscosity, mu del Vx. Suppose this is Vx is changing. Suppose this is the flat plate. Okay, now fluid is striking this surface. Now, before this striking this surface, the fluid had the uniform velocity. Now, once it will strike the surface, what you will find that this surface is stationary. So, due to no slip boundary condition, whatever air molecules will come into contact with this stationary surface will become stationary. Okay, so will become stationary. So here velocity of the air molecule will be 0, and after that you will find it will increase in this direction. Okay, because at the wall the shear stress would be highest, so it will increase, then velocity will increase in this direction and will reach at the free stream velocity. Suppose this is b infinity or b fluid, we sometime write b fluid, so v fluid velocity. So this is the velocity profile at this section, especially at x is equal to something, let's say x dash, you will find this velocity profile. Now at this point itself, you will find this boundary layer thickness like this. Now, since all the layers are not moving with the same velocity in this zone, so what you will find the velocity gradient in this boundary layer. Above it, you will not find any velocity gradient, because you will find the uniform velocity. So no velocity difference, so hence no velocity gradient. So no velocity gradient. So no, this is the direction y, let's say, and this is the direction x, and we are taking this is the vx x direction velocity. So same thing in the y direction. So del Vx over del y. Now this del V over del xy is equal, del Vx over del y is 0 uh, above the boundary layer because B is same above the boundary layer. Within the boundary layer it will have some value, means within the boundary layer it will have the uh, this will have the this will have what? Within boundary layer, you will get the shear force. You will get the shear force. Above boundary layer, you will not get the shear force. Now the velocity, since velocity is increasing when you move from plate to above in upward direction. So we consider generally when this is free stream velocity, let's v infinity. So if the velocity reach up to 99% of this v infinity, so this is called the boundary layer thickness. Same is the definition with the thermal boundary layer. Suppose this is the hot surface and this is the hard surface, so TW, and suppose your fluid is coming with some temperature TF or T infinity CP, sometimes we represent free stream temperature. That's why we are using infinity subscript. Free stream means free from all restrictions, all shear forces, frictions, etc. Okay, so this fluid is moving. So eventually, when it comes into contact with TW, the temperature will be higher TW. Now, and once it will start, then it will start decreasing. So at this section, if you will find the temperature is decreasing and it will reach of decreasing, then it will reach equal to T infinity. So wherever you will find the temperature 99% of T infinity, then it will be the thermal boundary layer. Okay, so this is the thermal boundary layer, very similar to hydrodynamic boundary layer. In the thermal boundary layer, you will find the temperature gradient, and hence you will be able to calculate the heat flux. Above it, you will not find. You will temperatures are same, so no heat transfer above boundary layer, so no heat flux. Did you get it or not? Now let's move into this boundary layer. Is it visible to all of you? This PDF is visible to all of you?
Yes,
Hello.
sir.
Yes, sir.
हाँ, तो इसमें देखो बेटा, हमने यहाँ पे वेलोसिटी बाउंड्री लेयर बनाई हुई। यहाँ पे आपको पैरेलल लाइंस दिख रही होगी। ऑन द y axis we have taken the velocity in the x direction, and the x axis the x length is taken, length of the flat plate. Now what is happening that here is the uniform velocity bxf. Now you will see this boundary layer is developing. Now you will see the velocity is increasing from bottom to top. At the bottom the velocity will be 0 due to no slip boundary condition. At the top, since there is no friction, so velocity will be maximum and it will be equal to, of course, the free stream velocity. So this is the and this is the thickness, delta x is the boundary layer thickness. Now since dx is changing in the direction of y, so we have represented dx as a function of y. Similar thing will happen with tf, okay. So temperature of the fluid is tf, here is the uniform temperature. So when is this fluid with temperature tf strikes with the solid waste surface, so solid waste surface at higher temperature, so, due to new solid boundary condition with respect to temperature as well, the layer nearby the solid, try to attain thermal equilibrium with the solid surface, and temperature will be equal. So you can have a larger vector at this side at the bottom, and then slower vector, and then less length vectors on the top, and it will be approaching asymptotically, at the temperature Tf. Okay, that is the fluid temperature. So temperature is changing at any section x, as a function of y. Okay, don't worry, you will understand it. Okay, your offline classes is also will be conducted. Okay, there I will explain on board as well. Okay, Now here I'm just telling you the concepts of these all these things. Now this in this boundary layer, since velocity is changing, so viscous forces are dominant in this boundary layer, and that's why you are getting this velocity profile. Okay, otherwise no velocity profile. You will find a uniform velocity. Now, how will you define the H? Now, H defining H, suppose heat transfer will take place from this solid. So, from this solid, heat transfer will take place at the surface with conduction mechanism, and in the fluid with convection mechanism. So, both heat will be equal. Now, if you equate, let me tell you. So, nearby layer of the fluid will be stationary due to no slip boundary condition. So in the fluid itself, conduction up to some length and then convection. So you will take let me explain this a bit. So suppose this is a solid surface. Now liquid fluid will also come to halt right here. So here since it is stationary, so heat transfer will take place through what conduction. So conduction के through होगा तो क्या होगा बेटा? U dot double dash heat flux through conduction in the fluid itself. क्या होगा? Minus Kf, fluid conductivity of fluid right here. Must remember, because fluid layers become stagnant due to no slip boundary conditions, and del T over del Y at Y is equal to 0. Here we are taking Y in this direction, X in this direction, so Y is equal to 0. This will be equal to, now this heat due to conservation of energy will be convected away. So convection. So convection, so what you can write here? H. Suppose this temperature, this surface have the temperature Ts and fluid have the temperature Tf. So H Ts minus Tf. So find the value of H from here, heat transfer coefficient. How will you be getting? H is equal to, from this equation, H is equal to, in the numerator, minus Kf. H is equal to minus Kf del T over del Y at Y is equal to 0 at the surface. Y is equal to 0 matlab at the surface, and Ts minus Tf. So tell me, since temperature is changing in the direction of X as well, okay, so we are taking here Y, Y is equal to 0, we are taking Y is equal to 0. So we have fixed the value of Y, but we have said nothing about X, means it could be, since this is a partial derivative we are taking, so it could be the function of X and Y. But we have fixed, since Y at Y is equal to 0, then H could be the function of only T X. X. This is the function of X. Getting it or not? समझ में आया कि नहीं आया? Means if I will move from this age to this age in the direction of X, H will change. So H will change. So H at any cross section will be the local heat transfer coefficient. And if you want to define the H overall, then it must be some average value of all this H. Getting it or not? So this is the function of X. समझ आया कि नहीं आया बोलो? That's why this is written. So minus Kf del T over del Y, Y is equal to 0. Ts minus Tf is equal to Fx, since temperature are changing with X. समझ आ गया? आ गया? Getting it or not? So this is the definition. Now since temperatures are changing with X, then H is the function of Fx. So average value of H is defined as average. How will you find H is changing with X? How will you getting the average? Average. See, since H is changing with X, so dx average dx. This is how you define the H average. Any functions अगर एवरेज fx फंक्शन है तो उसका एवरेज हम फाइंड आउट करते हैं कैसे? fx dx divided by dx. समझ आ रहा है? This is the statistics. From statistics you will know. समझ आ रहा है बच्चों? हेलो?
Yes, sir.
Yes, sir.
हाँ सर. हाँ तो h average we can find out. Why do you need this value of h average? Just because h is changing with x and we need the one value of x. So अगर हम कहें कि आपका परसेंटेज कितना आया तो 12th में ये बीटेक फर्स्ट ईयर में, तो आप क्या करोगे? अब एक नंबर में जरूरत है तो हर सब्जेक्ट के परसेंटेज का एवरेज लेके हमें बताओगे ना. समझ आया? So this is the kind of average we are taking. Now, one more terminology that I want to explain right here. Now, this is the plate. This is the plate. Now, this is at the entry edge and this is the exit. Now, this as x is equal to 0 and x is equal to L, what is this called? Since changing heat h is changing along this the length of this plate. So, one more definition. So, this is called the leading edge. Leading edge of the plate, and this is called the trailing edge of the plate. Trailing edge of the plate. Okay, means trailing edge is x is equal to L and leading edge is x is equal to T. Now one more thing I would like to define right here itself. Since temperature is changing with x and y both, you see. Okay, so x and y direction temperature is changing, so how will you define the average fluid temperature? Since fluid temperature is changing, so average fluid temperature, how will you define? So you must take the heat, and since velocity is also changing, so what you will take as a weight? वेट क्या लोगे? रो सीपी. रो भी चेंज कर सकते हैं, सीपी वी आर कुड बी द फंक्शन ऑफ टेम्परेचर. सो मैं जो उसको ले जाता रो सीपी, मतलब ये हीट हो गया. बी एक्स. एवरेज हम फाइंड आउट करते हैं वेटेड एवरेज. कैसे? वेट और वेट ऑफ द फंक्शन हम लेते हैं एंड देन सपोज दिस इज द फंक्शन एवरेज हम डिफाइन करते हैं, यू नो, एंड डी एक्स लिखते हैं एंड डब्ल्यू डी एक्स. सो दिस इज द वेटेड एवरेज. Have you studied this type of averages? Now here we take this weighted average. Now what would be the weight? Weight I will take जो quantity change हो रही है वो ले लो. Rho will change, Cp will change, T is changing, Dx is changing. So all these quantities are changing. तो अब हम क्या करेंगे बेटा? ये चीज हम वेट में ले लेंगे, बट हमें एवरेज किसका चाहिए? टेम्परेचर का. तो टेम्परेचर को हम बाहर रखेंगे, तो W क्या हो जाएगा? रो Cp Vx. W क्या हो जाएगा? Rho Cp Vx. Since this is changing with respect to x and y both temperature, so we will take here dx dy. Here too dx dy. So weight is what? Here weight is what? जो चेंज कर रहा है वो हम एवरेज ले लेते हैं. तो इसमें वेट क्या हो जाएगा? रो Cp T और Vx. चलो हम पुट करते हैं और देखते हैं क्या होता है. TF. नाउ एवरेज फ्लूइड टेम्परेचर इज इक्वल टू, इंटीग्रेट करेंगे किसके? एरिया एवरेज ले रहे हैं. एरिया रो CPT is the weight, Vx is also there, रो CPT Vx. Okay, but T I must take outside because T का एवरेज लेना है हमें, तो T as a function fx. So T, so rho Cp Vx T. Okay, and area average you are taking, so T. So W की जगह पे क्या है? रो Cp Bx है, ये T नहीं, रो Cp Bx. So here I am taking रो Cp Vx, तो हम लेंगे ही वेट, एंड वेट dx dy क्या है? dA. So we will take. Getting it or not, this type of mathematics? So A is the flow area. समझ आ गया कि नहीं? हाँ जो This average you got it? Now see here. Now, certain terms we are going to define. So, bulk temperature or the mixing cup temperature means whole molecules you will take whole fluid and then you will mix up. Then all molecules will come to at the same temperature. Will come to same temperature, and that same temperature will be called as bulk temperature. Now this is the bulk temperature or mixing cum temperature. So we just have explained TF bar X is equal to area average rho CPT Vx. In case of this cylindrical pipe flow, Vx is the function of Vx is changing in the radial direction. And fully developed flow, in case of fully developed flow, and if flow is laminar, you will get the profile, velocity profile as parabola u max 1 minus r square minus r naught square. I'm not going to discuss that because you must have studied in the fluid mechanics, and if you need it, I will discuss in the offline classes. Now, E is the flow area. If conduit is a circular cylinder, just you can put the value of dA right here, and you can evaluate that value. Now, film temperature. Now, film temperature is something. Now, arithmetic average between bulk fluid temperature, TF, and surface temperature. So, fluid temperature and TSC. Now, this TF bar is the fluid temperature, average fluid temperature, and our solid, this fluid is flowing with average temperature TF bar, and solid temperature is TS. So, film temperature, what is the film temperature? Just I have defined average of these two, arithmetic mean, because these two are only two numbers. Okay, so this since we have taken the average, so it will become direction independent, xy independent, and Ts is the surface temperature that is fixed. So Ts plus Tf by 2, arithmetic mean, and other one is weighted. This is also weighted mean, but weights were 1 right here. Okay, so let me tell you. Now this is the film temperature. Now certain numbers I would like to define. Prandtl's number. So Prandtl number, what is the Prandtl number? Okay, let me tell you. Prandtl number. Now momentum diffusivity. Okay. आपने फ्लूइड मैकेनिक्स में क्या पढ़ा है बेटा? shear force tau is equal to minus mu dvx over dy. ये तो पढ़ा है. अब क्या करना है हमें, इसको हम रो से डिवाइड कर दें, म्यू बाई रो, और यहाँ पे भी कर दें. So what will happen? This mu by rho is mu. This is the momentum diffusivity. Getting it? Px by rho and dy. If rho is not changing, so this is momentum diffusivity. Okay, these are the same unit as thermal diffusivity. Now in thermal diffusivity, I told you that K by rho Cp is the thermal diffusivity alpha. Getting it? So momentum diffusivity, this is the ratio of momentum diffusivity, and so Prandtl number is the both, since both have the same unit, this alpha have the same unit as mu have momentum diffusivity. So Prandtl number is defined as numerator में वही की quantity लेंगे mu and alpha लेंगे तो same, both have same units, so dimension will cut. So this Prandtl number will be the dimensionless number. Now this mu is mu by rho, and this is k by rho Cp. Now tell me, this rho will cancel. So what will you get? Mu Cp by k. Mu Cp by k. So this is the Prandtl number, mu Cp by k. What do you know by Reynolds number? Reynolds number is rho Vd by mu. So Reynolds number is rho v velocity d characteristic diameter by mu. Now mu by rho is mu, so you can write Pd mu by rho Vd by mu. So this is the Reynolds number. So Prandtl number, Reynolds number. One more number I will be getting, since you have seen that this is the surface, solid surface. Fluid is flowing with some temperature less than this Ts. Tf is less than Ts. So heat will transfer through convection in the stationary layer of the fluid due to no slip boundary condition, and then through convection. So the ratio of these two since heat transfer fluxes have the same unit, so ratio of these two will become one more dimensionless number. So that is called the you know this Nusselt number. So Nusselt number is Q S double dash convection divided by QS double dash conduction. So expressed at surface means surface we at the surface we are finding out. So S delta T is the convective heat transfer, convective flux, and minus K dt or d is the conductive flux, and this will give you S delta T. And since we are taking at the surface, it's also K delta T or d delta X. We can write dt or dx as delta T or delta X. Delta T will cancel out, hence we will get S delta X by K. So this Nusselt number is Nusselt number is H delta x की जगह पे हम L लिख दें तो K HL by K. Now you know the correlation you will find out Nusselt in terms of Nusselt number. Then you must be happy because you will put the value of you will get the value of H right from here. Okay, so Nu must be the function of something, some other dimensionless number that I will be discussing very soon. So experimentally, what has been found? So Prandtl number, Reynolds number, Nusselt number. Now, so the combination of these. Now, Stanton number is defined as Nusselt, Reynolds, Prandtl. Nusselt को अगर हम Nusselt number को हम divide कर दें Reynolds और Prandtl number just I have discussed, then this will become Stanton number. Another that this is dimensionless number, this is dimensionless number, this is dimensionless number. So Stanton number is also dimensionless number. So these are the dimensionless numbers pertaining to the convective heat transfer. Now, analytical solution. Let's find out the analytical solution. Now, from fluid mechanics, I am again using the fluid mechanics. So, from fluid mechanics, suppose flow over flat plate. So, flow over flat plate. So, velocity and temperature profile you will be getting from the equation. You must have this read these equations in the fluid mechanics. So, Bx del Bx over del x plus Vy del Vx over del y is equal to minus 1 upon rho del p over del x plus mu del 2 bx over del y square. Now you must understand if pressure is constant throughout the flow, then del p over del x, the pressure gradient will be 0. Now why we are doing this, we must understand very soon. Now the for temperature boundary layer, very similar equation you will be getting. So Px del T over del x, in place of Vx we have the T, plus Vx Vy del T over del y is equal to in place of momentum diffusivity mu, you will be getting thermal diffusivity alpha del 2 Ta over del y square. Now, why we have not taken pressure gradient, because so that both these equations for the velocity boundary layer and thermal boundary layer look similar, so that solution will look similar. Because so there is a additional term, so pressure gradient I will make the 0 for simplification. Now since dx and t have the same functional dependency, so solution will be look like same. So dx is some function of y and t is also some other function of y, but they look both similar. Now since you see this is the equation, so dx में partial है तो x में and y में equation, this is the second order del 2 bx over del y square. So you need to solve this equation. So you will have the 4 boundary conditions, 2 at the bottom of the plate and 2 boundary condition at the boundary at the hydrodynamic boundary layer, top layer. Okay, 2 boundary conditions. 4 boundary condition means you must have the 4 arbitrary constants. Solution will must have 4 arbitrary constants. So we can construct a polynomial of degree 3. So degree 3 is c1 plus c2y plus c3y square plus c4y cube with any polynomial. Now since this contains the 4 arbitrary constants, so solution means it could be the solution. Now only we need to find out the value of c1, c2, c3, c4. Now it must satisfy the boundary condition as well as these two equations. So at y is equal to 0, two conditions. At y is equal to 0 means at the flat plate, you must have the Vx is equal to 0 due to no slip boundary condition, and del 2 dx or del y square. See, shear stress at the wall is not 0, but rate of shear stress is, but the shear stress gradient is 0. Okay, so del 2 Vx or del y square is equal to 0. At y is equal to 0, the delta means at the top of the boundary layer, you will find bx is equal to bf, means the velocity in the x direction will be equal to the bf, means velocity of fluid, because that's the definition of boundary layer. 99% of the fluid velocity it will become, means almost equal to the fluid velocity. So bx is equal to bf and del vx over del y, hence the velocity gradient is 0. Now by applying this condition, means at y is equal to 0 boundary condition, if you put then this bx is equal to c1 plus c2y plus c3y square plus c4y cube, we will get c1 and c3 will be 0. Now you will find with the other two boundary condition the value of c2 and c4. Once you put, it will be the function of delta bx vf. So if you put the y is equal to delta bx is equal to bf, this one, then you will be getting C2 plus C2 delta plus C4 delta cube is equal to Vf, and y is equal to delta b del Vx or del y is equal to 0, then you will get the C2 plus 3C4 delta square, and here you will be getting the solution, the value of C2 and C4. Okay, C2 you will get 3Vf by 2 delta. After solving these two equations, very simple. C4 is equal to minus Vx by 2 delta cube. Therefore, velocity profile becomes, Bx by Vf. So you will put the value of C1, C2, C3, 4, C3, C4, all you got, and in this equation Bx. Okay, so you will get this profile, and you will divide after putting these value of C1, C2, C3, C4. You will divide by Bf both left and right hand side of the equation. Then you will get Vx by Vf is equal to 3 by 2 y by delta minus 1 by 2 y by delta cube. Now, okay, so this is the velocity profile. Since these two equation, if you look, these two equation look similar, so only you have just replaced in place of Vx the temperature, so the solution will look like similar. So temperature profile you will also have this right hand side same. So right hand side same, 3 by 2 y by delta dash minus 1 by 2 y by delta dash cube. So thus you will get this. But this is the excess temperature T minus Ts and divided by Tf minus Ts. So this is the dimensionless temperature that we are taking, dimensionless temperature, because here dimensionless velocity Vx and Vf is the velocity dimensionless. So this dimensionless temperature must be there. Okay, now if we move towards convection, I told you now I'm going to I have defined all the Reynolds number, Prandtl numbers, etc. Now I would like to define correlations. So correlation, natural convection, or T is changing, then rho is changing. So by rho changing, we must change to conserve mass flow rates. Now natural convection, since volume expansion coefficient, so its general tendency when you heat up something, it will expand. So volume expansion coefficients beta is equal to 1 upon b del v or del t p at constant pressure. Since volume is increasing with increasing temperature, so this should be already positive. So we don't have to put negative sign if we are expressing in terms of volume, because tendency of fluid to expand when heated. Now, but if you are representing in terms of density, then you will find that temperature, with increasing temperature, density is decreasing. So this will become negative. So hence you will you must put the minus sign before this to make it positive. Now a very good parameter, good dimensionless number, that is defined as Grashof number in terms of this beta. Now this G is the gravitational force, beta is the this volume expansion coefficient, and Ts minus T infinity is just the surface temperature, and T infinity is the free stream temperature. LC is the characteristic length, just like plate length. Okay, and diameter of the, if inside pipe heat transfer is happening, then diameter of the pipe LC cube by mu square. This is the dimensionless parameter called the Grashof number. Very important and central parameter, because beta is central parameter with respect to natural convection due to density variation. Hence Grashof number is the central dimensionless number with respect to what? With respect to natural convection. So for ideal gas, if you P is V is equal to nRT, P is equal to rho RT, if you calculate the beta, you will get the value of beta is equal to 1 by T. Now the correlation looks like Nusselt number is equal to C Rayleigh number uh, based on length of the plate. So Rayleigh number is Grashof number I have already defined, and Prandtl number. This is the product of Grashof number and Prandtl number. Now if you know the value of Nusselt number, so Nusselt number is SD by K, HL by K. So you can calculate the value of S from this equation. And in case of forced convection, you will get the correlation like Nusselt number. This is the product of Reynolds number and Prandtl number, power sum m and power n. That would be found from experiment. Okay, you can get the value of these powers from experiment. Okay, so this is the free convection and forced convection. Now let's return to condensation. Now, as far as condensation is concerned, what is condensation and when this happens? Okay, so for condensation, you must have some solid surface. That solid surface must have less temperature than the with respect to fluid, because whatever vapor you want to condense must have higher temperature and solid must have lower temperature, so that heat transfer would take place in the direction from vapor to solid surface, and thereby decreasing temperature, and hence condensation will take place. Now condensation will take place, now I am talking about vapor. So at pressure you can fix its saturation temperature. Now vapor must have some saturation temperature corresponding to its pressure. Now let's say its pressure is PS, saturation pressure is PS, and saturation temperature is TS. Now this solid surface have the temperature TW, okay, wall temperature and like that. So this have the temperature TW. Now it will condense over this surface, since this surface have the less temperature than the vapor. Now what will happen, that a boundary layer would be developed around this vertical plate, and this boundary layer thickness, let's say delta. Now whatever assumptions, now film condensation and drop wise condensation, there are two type of condensation, film wise and drop wise. Now what will happen, once vapor will condenses over a surface, vapor will condense over a surface. So if vapor will condense means liquid droplet, vapor will converted into liquid droplet. Okay, so once it will be converted into a liquid droplet, it may happen that liquid droplet will individually, it will remain in the form of drops. In the form of drops, it will not become like film. Means it will not cover the whole surface of the solid. Okay, so film is something, film का मतलब क्या होता है, film का मतलब होता है that will cover the entire surface, that is called the film. Okay, so here the drop at different places, discontinuous places, you will find the drop. Now once drop, you will find some drop may combine, and after combining you will find that its density, its mass will increase, and once mass will increase, then you know that gravity is acting towards the z direction, negative z direction, the positive z direction we have taken towards this, and this is the positive. This is our frame of reference of analysis. So what we are doing, that if mass will increase, then gravity will increase, and then drop will fall. So this is the drop wise condensation. Now what happened in the film wise condensation, that a complete this surface will be completely covered just like a film when vapor condenses. Okay, so there will be film. So that is the film condensation. Now if you do the experiment for film wise and drop wise condensation in terms of heat flux, what you will find, that heat flux in drop wise condensation is more than in the film wise condensation. But it is very difficult to maintain the drop wise condensation for a long time, because you will find initially drop wise condensation, but later on it will become the film. Okay, so what means industrial process where condensation will occur. We analyze the process based on film condensation. Now, in case of film condensation, now in this film, whatever we have, okay, this film, what we take some assumption to analyze this. Now, Nusselt was the scientist who analyzed this in a very deeper sense, and he has taken some so many assumptions. Now he has taken fluid properties constant. Now this assumption is pretty good. Why? Because in this boundary layer thickness, you will find this thickness is not very much high. So in this boundary layer thickness, you will find almost not much variation of the temperature and all those things. Now most of the properties is dependent on the temperature, intensive thermodynamic variable. So fluid properties will remain constant. This is pretty good assumptions. Okay, now this is the solid and vapor, this is the liquid vapor interface. Now at the interface you will find the saturation temperature. This interface would be at the saturation temperature. Now one more assumptions that we are taking, that momentum effects are negligible. What is the significance of that? You must have studied in the fluid mechanics the momentum balance. Momentum effects negligible means momentum out and minus momentum in is equal to the sum of the external forces acting in that direction. Now what are those forces? In case of the fluid, you will find these are the two types of forces: body forces as well as surface forces. Here the body forces will be the gravitational force, okay, and surface force. So all those forces will sum up, since momentum effects are negligible, so no momentum in and no momentum out, so right hand side will become zero. So we will take next, shear force is negligible at the interface. Since at the interface you will find that velocity of the vapor and vapor liquid interface, you will find the velocity is same. So since the velocity is same, there is no velocity gradient, and shear force is defined through Newton's law of viscosity, means del v, del vx over del y, whatever the velocity gradient. Since velocity gradient is zero, so shear force we can neglect at the interface. Now next thing is that temperature distribution. He has assumed, Nusselt has assumed the temperature distribution within this film is linear. Linear means it will change from TW at this plate to TS saturation temperature linearly. Okay, and enthalpy associated with the subcooling of the liquid are negligible, because it will be negligible with respect to what? Latent heat of condensation. Okay, so we have now next what we will apply. What Nusselt has done. Nusselt has applied the condensation and the basic principles of the heat transfer, means mass balance and then heat balance and momentum balance. Now with the respect to mass balance, now this is the z direction I have taken, downward direction, and this is the y direction, and perpendicular to this plane we have taken x direction. Okay, let's say b, capital B is the width. So per unit visit, mass flow rate per unit visit, m dot b is coming in, and m dot b and plus d change in this d m dot b, that is coming through, from the interface, that red line you are seeing, d of m dot b is equal to this I will derive very soon. This is added through condensation. So this is the mass balance that we are applying. Now let's come over to the momentum balance. Momentum balance is nothing but this is the Newton's second law. So for the control volume dy dz, we have taken this is the dz in this direction and dy in this direction. Okay, in which direction we have taken the thickness. So dy dz, you will find the net z direction forces, surface forces, shear forces, and body forces, gravity forces. Now z direction momentum leaving the control volume and z direction momentum entering the control volume. Since we have taken in assumption momentum effects are negligible, if you see this third assumption, momentum effect is negligible, so right hand side will become zero. So right hand side will become zero. Now if you see this left hand side, net z direction forces, so we have taken this control volume dy dz, and on this face what would be the shear force? Mu del vz over del y dz, and on this direction when you traveled in the distance dy, you will get mu del vz del y plus del 2 dz del y square dy dz. Dz is the area, because unit thickness we have taken. So dz into 1 would be the area. So you see, this is from through Taylor series. Taylor series expansion at this distance. If you know the value of z is equal to this distance, if you know the value of the function, then at z plus dz you can get the value of the function. Now, and this is the body, this is the surface forces, shear forces on this face and on this face, and the gravity force is rho dy dz g. This is the body force, rho dy dz. Rho is the mass per unit volume, dy dz is the volume, because we have taken unit thickness, so dy dz plus into 1. So this will be volume. So mass per unit volume multiplied by volume will give you the mass, and then multiplied by g, it will give you the body force of gravitational force. So these two body forces and gravitational, this and this is the plus z direction. Plus z direction downward I have taken. So opposite to it will be the minus z direction. So we are making the force balance in the z direction. So you will get in the downward direction we have taken positive z. So rho dy dz g, this plus mu del vz over del y. This would be positive, plus del 2 vz or del y square dy dz, minus on this face, shear force on this face, minus mu del vz or del y dz is equal to 0. Now if you simplify this, you will be getting del 2 vz or del y square is equal to minus rho g by mu. Now since this is the second order differential, partial differential equation, integrate, you need to integrate it twice to get the solution. So once you integrate first time, you will get a del vz del y is equal to minus rho g by mu y plus c1. Then again integrate it to get the value of velocity profile. So dz is equal to minus rho g by mu y square by 2 plus c1 y plus c2. Now at y is equal to 0, now apply the boundary condition to get the value of c1 and c2 arbitrary constants. Now at y is equal to 0 means at at the vertical plate itself, this y, and I am taking in this direction y. So at y is equal to 0, dz is equal to 0 due to no slip boundary condition, and at y is equal to delta, del vz over del y is equal to 0, because shear stress at the interface, in the assumptions we have taken, vapor liquid interface, shear stress is 0, okay, because of same velocity at the interface, del vz over del y is equal to 0. Now once you put these boundary condition, you will be getting c2 is equal to 0, and the value of arbitrary constant c1 is equal to rho g by mu delta. Now once you will put these values of c1 c2 in the vz, you will be getting the value of vz rho g by mu y delta minus y square by 2. So this is the velocity distribution in this liquid film. Now once you get the velocity distribution, you can calculate the mass flow rate. So mass flow rate of the condensate at the distance z from the top. So this is the distance z from the top, mass flow rate. What could be the mass flow rate if you get the velocity profile? So you will multiply Vz by area. Area we have taken perpendicular to the direction. We have taken B. V thickness is B. So B multiplied by dy will give you the area, and Vz is the distance per unit time. So this will give you volume per unit time, and rho से multiply करोगे तो mass per unit volume, so this will give you the mass per unit time. But you need to find out throughout, not bdy, but throughout this thickness. So y is varying since 0 to delta, so you need to integrate to get the total mass flow rate. M dot is equal to rho 0 to delta vz bdy. Now once you integrate it, now vz profile, you are getting this from this equation. Vz you have already you got already. So you must put the value of Vz right here. So rho 0 to delta rho g by mu y delta minus y square by 2 b dy. Once you integrate it, you will be getting the value of rho square g b by 3 mu delta q. Now it will be I want to divide it, since B is coming into picture, but we want to find out the mass flow rate per unit width. So what you will do, you must divide by m dot by b. Now you also want कि अगर आप z से dz distance और move करते हैं तो कितना mass flow rate में change हुआ, तो when you are moving downwards, this z at z to z plus dz, what will be the change in mass flow rate? So just you need to do del, you have to take differential of this. So d m dot v is equal to rho square g by mu del square d delta. Means what it indicates? Indicates that as we proceed downwards from a horizontal section z to a section z plus dz, the condensate film thickness increases from delta to delta plus d delta, and the mass flow rate increases by what? Rho square g by mu delta square d delta. In other words, you can say that condensation rate per unit width from z to z plus dz is rho square g delta square d delta by mu, because I told you from the mass conservation itself that dm dot b is the condensation rate. So condensation rate you are getting, this is the condensation rate by rho square g delta square d delta by mu. Now consider, now what we left, now we have applied the momentum balance, now we have to apply the energy balance. So energy balance, consider the same CV, control volume, and apply the first law of thermodynamics. Now enthalpy we are taking the fluid. Now since this is in, m dot b is in, so you need to multiply the enthalpy of the fluid, this mass into enthalpy, because enthalpy per unit mass you are taking, so you need to multiply with this m dot b, and similarly out, and this, so you will apply, you will just take the product with enthalpy. So this is the control volume leaves m dot b, m dot by v plus e m dot by v hf minus this, and hf by lambda, because this is related to the condensate. See, so right here, if you see this dm dot b, here you will find hf plus lambda, means latent heat of the condensation also, because here at this interface condensation will occur. So we are taking this is equal to, so if you solve this, you will get minus dm dot b lambda is equal to, now this, since this is the heat entering to the control volume, so this is the rate of heat enters to the control volume, right hand side minus k dt or dy, this from Fourier's law you will get dz, you will get from Fourier's law. So whatever heat entering into this control volume, okay, so this will be equal to that. So this is this you will get from the Fourier's law. So Fourier's law, if you apply this, now if you solve this, this you will get delta cube d delta is equal to this much. So you need to integrate with respect to delta, you will get this delta e power 4 by 4 is equal to k ts minus tw, okay, ts minus tw mu upon lambda rho square g z plus constant. Now at the top of the plate z is equal to 0. You must understand that this what will be the value of delta at the top of the plate. So at the top of the plate you will be getting value of delta is equal to 0. So what will happen, c1 is at z is equal to 0, sorry, at the beginning of the plate, at the top of the plate z is equal to 0, delta is equal to 0, because film thickness, see at this point z is equal to 0, z is increasing in the downward direction, so at z is equal to 0, what is delta is equal to 0 right here. So delta is equal to 0, through this boundary condition you will be getting the value of this lecture is fast, but I will revise it also in the offline classes. The purpose is to just cover the syllabus at the first side first. So what will happen that at the top of the plate z is equal to 0, delta is equal to 0, hence you will get the value of c1 constant, this value of constant is equal to 0, so delta e power 4 is, upon 4 is equal to this much, and from here you will get the value of delta. Okay, so this delta is equal to 4 k ts minus tw mu z upon lambda rho square g whole power 1 by 4. Now the local heat transfer coefficient H is equal to, now I want to get I get the value of film thickness. Now I would like to get the value of local heat transfer coefficient. So H is equal to heat flux at the wall upon Ts minus Tw. Just define the value of H earlier. So we use this definition to get the, so a heat flux at the wall I assume that temperature is linear. So K Ts minus Tw upon delta divided by Ts minus Tw. This is equal to K upon delta. C heat transfer coefficient is equal to K upon delta. So therefore now you got the value of delta in this equation. If you will put, you will get the value of H is equal to lambda rho square g k cube divided by 4 Ts minus Tw mu z whole power 1 by 4. Now see from this equation that h is proportional to z t power minus 1 by 4. Other things are constant. Now, so if you plot the curve between h and z, you will get this type of curve. Okay? Because h is decreasing once you increase the z. So average heat transfer you will get h dz 0 to L 1 by L. I have defined how to get the value of h. So you will integrate this equation from 0 to L. So once you integrate it, you will be getting h bar is equal to 4 by 3 1 by 4 e power 1 by 4 lambda rho square z k cube divided by ts minus tw mu L whole power 1 by 4, and this is equal to 0.943, and rest is lambda rho square g k cube divided by ts minus tw mu L whole power 1 by 4. Now at h is equal to z by L, just if you want to find out, so just put here z is equal to L, you will be getting this value. Z is equal to S. Bar is equal to 4 by 3, HZ is equal to. So this is the relationship you will get from above equation. So if you calculate the value of H Z is equal to L, you will get so you will get this value, and at this point you will get this value. So this is the equation. So average heat from the plate, heat flux you will be getting like this. Okay, local heat of latent heat of vaporization. Now boiling I will discuss in the next lecture tomorrow. Thank you. Boiling and radiation will be covered in the next lecture. Thank you.
Thank you, sir.